location. It's 9 o'clock here on the West Coast and noon o'clock on the East Coast, where John Dresty is attending and will be walking us through this webinar. I wish to thank you for joining us for this brief technology review session. It will be about a half an hour and will include at the end approximately 10 to 15 minutes of questions. I'd like to welcome your questions through submission via the webinar sidebar here, and you can submit them at any time, and I'll funnel them to John as the timing seems appropriate. You'll see the section on the sidebar there, and you just type your message in. So those of you that have many folks in attendance in one room, we welcome your participation as well. I don't know that you're all there, so do include your name when you submit a question if it's not included in the webinar. And with that, I'd like to turn it over to John. John Dresty joins us from Connecticut at the moment, and I'll pass it to you, John. Thanks very much.
Thank you, Max. I would also like to welcome all of you to this brief technology review. So let's get started. I developed this technology that we're going to discuss today at the University of Connecticut in the 90s, and I joined Griswold Water Systems in 2011, and Griswold Water Systems has made some very important advancements, both technical and commercial, in the marketplace. So that's basically what we're going to talk about today. And we have to start with a few words of vocabulary so that we all understand how this technology works. So what's in the water? Water has dissolved minerals in it, which the top bottle represents. It can't be seen, or these particles, minerals cannot be seen or filtered, but they are measurable by conductivity. The water also has in it a lot of blown-in dirt, which makes the water murky, and this is not measured by conductivity. These small particles that I just described as dirt are the key to wave water treatment. We would have to keep in mind the difference between these two types of substances in the water. Dissolved minerals like calcium carbonate are sometimes called dissolved solids, but they are not solids at all. They have become part of the liquid. Whereas blown-in dust and dirt are really true solids, and people often call them suspended solids. They're quite different from each other, but really both are necessary for wave treatment. So as the water, this is a summary slide that shows that as the water passes through the wave, it changes the relationship between dissolved minerals and suspended solids. It makes them behave differently. So the way to best describe that is that dissolved minerals tend to plate out. And in order for that to happen, you need to achieve supersaturation, which is the overload of too many dissolved minerals that have been concentrated by evaporation in the cooling tower. And that's because minerals don't leave with the water vapor that's evaporated. Instead, they just concentrate. And this problem of too many minerals dissolved in the water becomes a driving force. It forces the minerals to become a solid. However, a surface where the calcium and alkalinity, or calcium and hardness, or the hardness and alkalinity, or calcium and carbonate can meet. You need a surface for these two materials to meet. If that surface is an equipment surface, you get scale, as shown in the photograph to the right. If that surface is a suspended particle, you'll get powder, which is our objective. That surface scale can happen not only on the fill that you see on the right, but chiller tubes and all the equipment surfaces in a cooling system. This is a graphic which indicates that evaporation causes the minerals in the water to reach saturation, and so therefore we get this driving force to become a solid. The minerals are not shown in this graphic because they're invisible. They're part of the water. But what is shown is the scale on the edges of the pipe, which is what we're trying to avoid. And the small particles passing along with the water are representing the suspended dirt. There are many suspended particles present in the water system, and they would be a good site for calcium carbonate to precipitate or plate out. However, there's a problem. The naturally occurring surface charge that these particles have make it an unfavorable place for calcium carbonate to plate out. And that jagged white ring around the particle is intended to represent the static electric charge. As long as this condition continues, minerals are forced to find an equipment surface in order to plate out. This is a technical graphic which illustrates that point a little more in a little more detail. The dirt particle, represented by the large black sphere in the center of the graphic, has a negative charge. And the green particles are calcium ions which have a positive charge. The blue spheres are the bicarbonate ion, also could be considered a carbonate ion. And you'll notice the green ions have no problem getting close to the suspended particle because they have a plus electric charge and the particle has a negative electric charge. But there are no blue ones close to the particle. And without a blue and a green meeting at the surface of the suspended particle, the dirt particle, plating of calcium carbonate will not occur. That is the problem. That is what our technology changes.
And John, let me just interject here and say that at one point, Chris Mongo, you raised your hand indicating that you might have a question. For those of you that get questions as we go through some of the technology review here, please feel free to submit them to me and I'll compile them. It means you'll need to type on the keyboard and send it to me via chat or question. Thanks. Okay, keep going, John.
Okay, what the WAVE does is use digital processors to create a very powerful electrodynamic field. And the changing polarity of these fields removes that surface charge. The graphic shows that half the charge has been removed. And when it's completely removed, that particle becomes electrically neutral. Now we return to that other graphic, and now you can see what has changed. There is are approximately the same quantity of blues and greens touching the suspended particle. And that means that it's electrically neutral, and neither the calcium ion or the bicarbonate ion are repelled. And when that happens, you will find that the calcium carbonate starts to plate out around the suspended particles. And it actually prefers the suspended particle to the equipment for two reasons. One, there are so many particles, suspended particles, the calcium carbonate ions will become close to one very soon before it ever gets to the equipment. The second reason is that the particles and the ions are moving along with the water at the same speed, and that's an easier situation than plating out on equipment surfaces which are stationary. So as this process completes itself, it creates a harmless powder, which is basically limestone, And this particle of powder, which looks like a popcorn ball or a piece of cauliflower, continues to grow and grow and grow over time until it gets to be about 50 or 70 microns. And when it gets to that size, it will either settle in the basin or be removed by some sort of filtration. And we are quite convinced that centrifugal separation is the best method to remove it. So that is the basics technology of how the wave technology prevents scale. And so we've summarized 4 points here to take away from this part of the discussion. And I'll just read them and with a little additional emphasis possibly. We must operate at supersaturation because it changes the way the calcium carbonate behaves as it comes out of solution. This is extremely important that we must be at supersaturation so we are making powder. And how that happens is that the wave signal removes the surface charge on the suspended dirt particles and makes them the preferred place to plate out calcium carbonate. And number 3 is the reason that they prefer to make powder than scale up equipment is because they will encounter an acceptable particle before they ever get to the equipment, and because the relative velocity between the particle and the calcium carbonate is essentially the same. The calcium carbonate, as you can see, the particle is almost stagnant. It's moving along with the ions. So this makes a harmless powder, just a limestone powder instead of scale. So we'll move to the second key technological benefit of the wave technology, and that's bacterial control. And we know that bacteria is present in all drinking water, and it also enters a cooling system from blown-in contamination. The wave does an excellent job at controlling bacterial populations and keeps the bacteria counts extremely low. CTI recommends 10,000 bacteria, which are termed CFUs per milliliter, and the wave does substantially better than that. And we do so with 2 different methods of controlling bacteria. The first one is entitled encapsulation, and that's because, and what that means is that bacteria are themselves suspended particles with negative surface charges. And when those charges are removed, they could even be the beginning of a piece of powder where calcium carbonate plates out around the bacteria, or alternatively, they can be drawn into a growing piece of powder, as the graphic shows. The bacteria aren't killed immediately, but because they can't get nutrients to feed themselves or get rid of waste, it restricts their ability to reproduce. That is one of the main methods that we use to control bacteria. The second method is called electroporation, and for this one we use high-frequency pulses that damage the membrane walls of the bacteria. It creates pores and leakages from the bacteria, and they have to expend all their energy in trying to repair the damage. This also prevents them from reproducing. I'm going to move for a minute to another type of bacterial contamination, which is related to a biofilm. And this table, this graph, demonstrates the bacterial control from chemical water treatment, a fairly poor version of chemical water treatment, that on the left side of the graph shows bacteria counts that go off the graph into the millions. And then they're shock dosed with chemicals, and it's reduced to a more reasonable number below 10,000 bacteria per milliliter, which is the red line in the center. We installed a wave in this rather old and dirty system, and you'll notice that after the wave was installed, there was actually a spike in bacteria count. It went up to 20,000, but then rapidly dropped, and then there was another spike. And the explanation of those spikes are that when a biofilm dies, it releases bacteria into the flow of water. And since this was an old and dirty system, that first spike after the wave was installed represents the killing of the biofilm. It typically takes about 3 weeks. You would not see a spike like this if this was a brand new system, because there would be no biofilm. An interesting fact on this slide is that there's another spike later on, and this was an injection molding company which had one line of machines that were not running at the time we installed the wave. And when they opened that second line of machines, there was a second kill of biofilm. Once all the biofilm was gone, you'll see the very low levels of bacteria to the right of the graph. We're currently getting between 500 and 800 per milliliter, which is exceptionally low. That slide introduces biofilm. Biofilm is really quite a serious problem for cooling towers. It fouls the fill, and as such, it acts as a glue that traps dirt, debris, and everything that goes by, and it lowers the evaporative efficiency. It can very easily exist in the chiller tubes or heat exchanger plates, and it has 4 times more insulating property than actual mineral scale. It also can cause microbially influenced corrosion, which happens under a slime layer, which is one of the most serious types of localized corrosion that can happen in a cooling tower. And it also is a home for Legionella. And Legionella becomes infectious in the slime layer. So if there's no slime layer, no biofilm, there's no disease. This picture represents what a biofilm looks like, and the image to the right is a mature biofilm. That's what it grows into. And the most significant thing about this drawing is the water channels. Those holes in the biofilm are the pathway for food to be brought in to support the biofilm, which is a communal colony of bacteria, and it allows waste to be removed. And so the way in which the wave destroys biofilm over a period of time is it starves the biofilm, because the nutrient soup that is going through that water channel becomes too weak to support the biofilm. I'll also point out at the bottom of this graphic, it says that chemical treatments, disinfectants, have a very difficult time penetrating the biofilm because there's a protective canopy over it, which the bacteria secrete. So the question that becomes obvious here is, why is the broth, the nutrient broth that goes through these water channels, so weak and not able to support the biofilm? Well, I've already mentioned here that we consistently control bacteria population at low levels by avoiding population surges and subsequent kills of bacteria, which is what usually happens in cooling towers. So when this becomes, when the broth becomes too weak to support the biofilm, it starves and essentially falls apart. I changed a couple slides in order here, so I didn't really discuss that yet. But the I'm returning to this slide to show that what made the broth rich enough to support a biofilm were these big spikes in bacteria, the big population surges, which were then killed, and the dead bacteria and waste products from those population surges are what makes the broth rich enough to support a biofilm. And when you don't have a population surges and you are operating, when you are operating at the right-hand side of this graph, that is when the broth becomes too weak to support the biofilm. Okay, so the advantages of dealing with bacteria this way is that species of bacteria are really not a factor. All bacteria are treated equally by the wave. Bacteria can also not build up a resistance through mutation to the wave's method of disposing of them, unlike biocides, which are metabolic poisons. So consequently, there's no need to rotate biocides to keep them off, to keep the bacteria off base, off balance. There's no shock dosing to kill off those big population surges, which you saw in the graph. And there's no residual chemicals down the drain. And of course, you know, biocides are the most toxic and the most expensive chemical that's added to a cooling tower. You end up with very low consistent results. And this is registered with the EPA as a biostatic device.
Hey, John, Paul Prentice asks a question which I think you might have addressed, but I'm going to throw it out to you, and that is, you know, in terms of that graph which shows the spikes on biological control, why are there some spikes below 10,000 before the wave? Can you hit that again?
Sure. Once the bacteria gets quite high, there's maybe a once or twice a week shock dosing of another biocide to do a more effective kill. And it does do a kill of those major spikes. And they can't use that biocide all the time, both from the point of view of cost and damage to the equipment and safety. So every valley in that graph is due to shock dosing because there was a population surge that they had to deal with. If you don't have the population surges, you don't have to do the shock dosing. I think that's probably the answer.
Good.
Okay, let me see here. So what are the 4 points we should remember here? First of all, planktonic bacteria, that means free swimming. We have two methods. One method is encapsulation in the popcorn ball, but you have to be making powder for this to happen. But it happens throughout the cooling system, even many yards away from the wave. Electroporation is where we damage the membranes of the bacteria. You don't need to be making powder for that to happen, but this is only happening when the bacteria is inside the wave unit. And this is why you need recirculating water and multiple passes. So to have both of these mechanisms in play, you have to be making powder and you have to be recirculating water. Also, now we move to biofilm, which are called, or slime layer, which is called sessile, biological control, and the nutrient broth that feeds a biofilm is too weak to allow the biofilm to thrive. In a wave installation, you will not feel any biofilm by touch anytime. We promise you that. We've had thousands of installations that are guarantee that. And you end up with a very low biocounts, which are almost as low as drinking water standards, at least hot drinking water standards. Okay, so the questions are being saved, so I'll move on to talking a little bit about the product. The product is basically 3 units, as you see there, and the InstaAlert remote monitoring, the control panel, and the reaction chamber, which is the spool piece. It has 3 functions It prevents mineral scale, controls bacteria, and it allows the cooling system to operate in such a way that you get excellent corrosion. The InstaLert remote monitoring is now being incorporated into the control panel. I show this drawing, this graphic of the blowdown system just to emphasize that a really good functioning blowdown system is so important for success with the WAVE technology. And that, of course, is because it guarantees you're making powder. And as we've just said, you've got to be making powder. It's very important to do so. Okay. We've made some advances in the product. Griswold has made some advances. And these are the basic advantages. And I'm going to talk about each of them for just a minute in a subsequent slide. We have a 4 times stronger signal. We have InstaLert 2.0, which is remote monitoring, which is really unique in the field of water treatment. We have some advanced design features that make the product more shop durable. We have NEMA 4 reaction chambers and controller. We have intelligent design auto-seek feedback, which I'll mention. All the products are UL listed, and they all draw a very small 100 watts of power on all sizes. The WAVE having the strongest signal is a very important one, and it's 4 times stronger, but it creates electric fields that are many orders of magnitude stronger. And you can verify this by biological control. That's the easiest way to measure the impact of this stronger field, how low the bacteria counts have been driven. And you end up with very stable, steady state operation without any ups and downs in bacteria count or anything else. Now, the 4 times stronger signal means a bunch of things, and let's just say what some of these benefits are. You have more stable and stronger electric fields, and that allows us to have a full range of sizes from 2 to 24 inch are standard and are being sold and implemented now. It also, the big one on this slide is it allows for side stream applications. We can treat the water effectively on a 25% side stream rather than full flow in the condenser water recirculation stream. The bacterial control is amazingly low, as I've said. We can also do high nutrient load applications such as breweries and bakeries that have much nutrient air contamination in the air. And it also allows us to do gray water or recycled water as makeup. So it's 4 times stronger, but it's also a smarter signal. And what we mean by that is almost no heat is generated by any size wave. It draws about 100 watts. So there's no damage from dry operation. It does not need to be interlocked in a pump. It will not damage itself in the hottest environments that cooling towers exist in. There's no moving parts, so there's no ventilation openings in either part of our product, which is completely sealed. No weather protection is necessary for outdoor installation or anything that has water raining on it. Both the components are NEMA 4 or NEMA 4X. I would now just mention that the significance of no ventilation openings is that you have no fans, so you have no louvers to support the fans, no filters to support the louvers, and so it's totally sealed. The auto-seek allows field correction for a compromised signal. A signal can be compromised either by a metal pipe being very close to it or being shut off, and we can recalibrate it in the field instantly with a phone call. It's also tough and shop durable. We have a fiberglass reaction chamber rather than PVC. It has unitized flanges built in, which are easy to install and lower cost. Doing so gives you better thermal stability and mechanical rigidity, also better UV tolerance. the reaction chamber, the spool piece, is filled with epoxy, and because of that, we have additional strength and moisture protection on that. I have 2 slides here about our remote monitoring. First of all, the purpose of this is to maintain good, stable performance in between certified human visits, certified service partner human visits. And so the InstaLert warns of potential problems before they become a problem. And it allows for a very quick dispatch of human service, and the opportunity for things going out of control as an excursion is really, really reduced. It's based on 3G and 4G cell service. It's good for international markets, for those of you that are tuning in here from international places. It reports any problem to the rep, the operator, Griswold Water Systems, and our certified service partner. It has 4 analog and 8 digital inputs, and we use 3 of them at this time. I mentioned that it's being included in our control panel, so you see the circuitry there on the right. It's pre-wired, so there's reduced installation costs, and these other bullets indicate what it actually measures. It measures the proper wave signal for effective water treatment that was set at the factory. It measures conductivity, which is crucial for making sure you're making powder. It measures the confirmation of flow in the system to avoid stagnant water, which is the enemy of all water treatment. And because of that, it is able to infer blowdown functionality by monitoring these things on a daily basis. We not only get an email when they go out of, if they go out of specification, we also monitor the data once a day. The 4 points you should remember about the product is that the Wave has the strongest signal of any pulse power product, and the big advantage of that is side stream applications and being able to deal with high nutrient load applications. The InstaLert remote monitoring is included with every Wave with no upcharge, and it diminishes the possibility of system excursions, and it gives you good control in between human visits. The Wave is exceptionally strong for the reasons that I said earlier, and the AutoSeek, or intelligent design, allows any kind of a problem to be detected and remedied on site very quickly. And so that's it. Now we're ready for any questions that you may have submitted, and so I'll turn it back to you, Max, to indicate what there might be.
Sure, thanks, John, and thank you all for participating in this. As you know, we like to do these webinars from time to time. I think increasingly you'll see them become a more regular part of our offering. We're looking at webinars every 2 months approximately. So as I review a couple things here, please do submit your questions. We have the 1 question already from Paul Prentice, but no additional questions posted thus far. This is your chance over the next 10 minutes or so to ask questions. You can either indicate that you have a question by raising your hand and I can unmute your phone, or you can type your question in the question bar on your control panel. We will have upcoming webinars, like I said, in that about every 2 months, and I think the next one will focus on either water savings potential or the ROI payback tools. One of the things we've seen in the market is that increasingly water savings and the costs associated with wastewater as well are a very significant need for customers, and certainly on the payback side, as water systems and cooling towers specifically use an immense amount of water. Okay, so any more questions here? I'm gonna pause for just a minute or two and allow you to type in some questions or raise your hand. Haven't seen anything at this point. We've got a question from Don Battershell. He asks whether this webinar will be posted on the Griswold website. Don, I have recorded this webinar, and so probably what we will do, because of the technology, it's not necessarily as easily accessible to the regular marketplace and engineering community. We might put this on Gris Tools instead. Haven't made that decision yet, but either way, you all will get a copy of this emailed to you. So you'll have reference to this, and we'll make this available at some point. A question for you, John, from Jim Gallagher, and he asks whether the bacteria create an odor over time. Good question.
Yes, yes, Jim. The bacteria under wave treatment doesn't really create an odor because it's there in such small quantity. What happens is that the bacteria live out their normal lifespan of 24 to 48 hours, and then they are just encapsulated as dead bacteria in the powder, and they leave when the powder is removed. And there's so few of them in there, there's no noticeable way to even know that they're there, either by touch or odor or any other way. So the water looks exceptionally clear, and you know, people that have more courage than I actually have drunk cups of it when it's under pulse power treatment. So not a problem, really.
Good question. And Natalia from España asks a question. She's wondering that when she does some startups periodically, and Natalia might need some clarification here. You say that when you do startups with Quimic, you get foaming. I don't know what Quimics are, but foaming certainly is not an issue with wave. I can let John address that specifically if you want to. Foaming is usually an issue with other chemical additives. So if there are no chemical additives, foaming subsides. Do you want to add to that, John?
No, I think that's the answer. Foaming is a characteristic of certain chemicals that are put in, and for the condenser water part of a cooling system, the wave is completely chemical free. There are some preliminary chemical treatments that still should be done to a chemical cooling tower when it's a brand new one, such as a chemical clean and flush. But for routine operation, there's no chemicals put into the tower, and so there would be no foaming at all.
Good. And David McDaniel, thanks for your question. How do we get the most up-to-date presentation? I think the best way to do that is to make sure you have access to this periodically through email. It's probably the easiest. I think we'll also end up posting this on Grizz Tools, which we haven't done yet. So it's a good question. We'll address that, and we'll get these posted to Grizz Tools so that you can log in and download the latest. It's probably the best. John Fuller, thanks for your question. He asks, does the control panel monitoring require a subscription-type billing, or is it available as a one-time cost? John?
Yes, well, it does require a subscription billing, but with every wave, we pay for 3 years of cell phone fee. It's quite low priced, but after the 3 years, it would be up to the customer to continue that. Good.
Okay, Jim asks a question. If untreated by a wave unit, can the accumulated bacteria create an odor? So we had that question already a little bit, but it was more related to.
Yes. Well, first of all, under chemical treatment, you do get biofilm, and you do get a lot of bacteria. And so, just to give you an idea about this, CTI says that you should have less than 10,000 bacteria per milliliter. And if you achieve that number, which chemicals have a hard time doing, you won't have any odor. But it's very common.
John, sorry to interrupt. John, I'm going to put you on speaker here so that you can ask your question in case we're getting it wrong. Let me unmute you, and you should be live now. Can you ask your question a little bit more clearly if we're not getting it? John, you there?
Me?
No, John Fuller. I've unmuted John Fuller just to make sure that we're clarifying his question.
You clarified my question.
Yeah. Okay. Let me just continue just a bit on that. In that, if you get 20,000 bacteria per milliliter, you probably won't have any noticeable odor either. Now, when you have a 50,000 per milliliter, it's going to be nasty. And if you get above 50,000, which is common to 100,000 or more, it's going to be disgusting. So there's a lot of odor issues that happen at high numbers, but really nothing below 10,000 per milliliter.
Good. And as a follow-up to the foaming question, Mike Jakubowski, our service partner manager, who is a former chemical guy, says that, in fact, the foaming is often related to the release of organics, which I believe Mike may or may not have something to do with chemical additives as well, but apparently the biological growth can create that foaming. We have a good question from Jimmy Hunt here. He asks, does the frequency of sand filter backflushing create a problem maintaining conductivity levels and ability to make powder? So I'll take this one, John, if that's all right here. In cases where you have wave treatment, for example, with sand filtration, either Griswold supplied or not Griswold supplied, and of course we don't recommend sand filters because of maintenance issues with fluidizing the bed and changing out that media, and also primarily water loss. That's why they're not recommended. Yes, it can create issues, but those issues are usually more problematic on smaller towers and when backflush is timed inappropriately. So you'll often get issues with sand filters on certainly smaller systems, 400 tons, 500 ton systems and smaller, where conductivity never reaches saturation. And that's because there's too much water loss within the system. So that can be an issue. On larger systems, it tends not to be. And of course, that's a function of the backwash timer, which can be a concern. So again, not advised from a Griswold standpoint to use sand filters. But if they are in place, you have to monitor backflush times and be aware of that. You want to add anything to that, John?
No, I think that's just right. Except that, we can use conductivity to make sure that we stay in saturation, except in those small systems. So in a small system, if you can achieve a saturation to begin with, we can probably use conductivity so you don't lose it. The problem is that if you never get to saturation ever, that's a problem because you have to be making powder.
Good. And I'm going to take two more questions given our time here. I'm sensitive to your time. One is a sales related question from Don, which I'll save to the end here. But Jimmy Hunt asks a follow-up question. Do we need to supplement the system with chemicals to build up conductivity levels on new installations prior to all equipment coming online? A very good question.
Yeah, that's an excellent question, and that sort of depends on timing. If the water is if the system is going to be wet and not put under load for some period of time, for a lengthy period of time, let's say more than 2 weeks, you do need to supplement it with chemicals, especially on the first season. You have to have corrosion inhibitor. And we try to make it so that customers don't leave a wet system without a load for 2 weeks. But if they must, then we have to add corrosion inhibitor. Typically speaking, you don't have to add it the next year because once you shut it down with saturation, the saturation will hold over the winter and you wouldn't have to do that the second year around. There are other issues about free cooling and about replacing the water in the fall that we'd need to speak about specifically, but generally speaking, it's that avoiding red water on the very first season of a new installation if it's going to be wet and without load for a long period of time.
Very good. And John, did I ask the question from John Fuller about subscription monitoring? I did ask that, right?
Yeah. Yes.
Okay, good. And that was answered. So I'll put the hand down here on the webinar. Last question from Don Battershell, which is a good one, and I'm not sure we're going to address it today, but he asks, what are the major talking points to present to a first-time customer who has had conventional water treatment issues? And this is an excellent question, John, and it really goes to the heart of selling this product. So I'm going to give John a chance to just hit this briefly with a highlight, but I want to follow up and say that in future webinars, we'll be doing sales-specific training related to exactly this kind of question. So this was really intended to be more of a technology review and a product summary and overview, especially for those of you who have new employees in your rep firms. And also review is always good, but in the meantime, John, you want to take a stab at answering the initial question?
I think there's two tiers to answer that question. First of all, I think what you have to demonstrate to a customer is the reasons that the benefits and reasons why someone would want to use this type of technology, which include better and more stable performance, environmental benefits in terms of avoiding chemicals exposure to the environment and to people, and good and being a cost-effective solution, a better solution from a financial point of view, and the one that has become really prominent lately, which is water savings. It saves an enormous amount of water, and so once you get through those 4 benefits and reason why to think about it, then we have many different sound talking points or sound bites in different formats that say, well, okay, how do we do that? What are the benefits that really cause those things to happen? And then you can talk about a strong signal and a 25% side stream. You can talk about remote monitoring. You can talk about many of the things we discussed in this slide presentation, in this webinar. And our marketing director, Carol Templeton, has many versions of this that are short, medium, and long that she can provide to you on this topic. And so I would say, Max, that we would probably email this question to Carol, and she will come up with an appropriate version of the answer.
Very good. It can be pithy, or I should say poignant and straight to the point information. Now, many of you, we're past time here. Jimmy Hunt had one final question that he got under the wire, but those of you that need to leave, feel free to do so. I know the timing we're going over a little bit here, but it's a good, more technical question, and I want to give Jimmy the chance to get an answer here. And the question is, do we recommend coupon racks to substantiate corrosion control? Now, John didn't get detailed into corrosion, and that might be an entire subject saved for later, but you want to address that on the rack question?
Sure. It's a quick answer. It is a big subject, and probably it should deserve its own webinar, but in terms of our recommendation, we don't recommend them for a couple of reasons. One is that they're easy to give. It's very easy for you to get bad information from them, either accidentally or in case somebody wants to give you bad information on purpose. And the other thing is it really doesn't tell you much about the serious types of corrosion, which are localized. It really tells you only about uniform corrosion. So, and the way we control pH on a monthly basis is by verifying that we're making powder and by verifying that the pH is appropriate. So we don't think we need coupons. And it's an expense and it's just a distraction. But if a customer wants them, we've developed a good third-party source of providing them and analyzing them. We don't even touch them. And if it makes a customer feel better, we can provide good results with corrosion coupons, and we're happy to do it, but we don't recommend it.
Very good. Well, thank you all. Excellent questions. I appreciate your attendance on behalf of myself and John Dresty and the entire Griswold Water Systems crew. I thank you for attending this. I hope the periodic technology and sales review is helpful. As I mentioned, in the next 2 months, we'll host another webinar, probably on a Friday, and we'll begin to get into both water savings, ROI, and payback tools as well from a sales standpoint. If you have topics or suggestions for future webinars, please email them to me and or Carol Templeton, and we'll make sure that we factor those in for future webinars. In the meantime, thanks again. Any final closing comments you might have, John?
I just want to thank everybody as well. I hope you found this useful, and I would echo what Max just said. Tell us what you'd like to hear on these webinars, and we'll try to provide the kind of information that's needed out there. So please do communicate with us on that, and thank you.
And as a final comment, I'll just say that we will be emailing a copy of this presentation to you. It'll have audio and the visual slides as well that you can watch at your convenience. And we will talk about, or at least try to implement, a posting of the same presentation online, probably through our rep tools section on the website, available via the website. Okay, and with that, thanks to all one final time. Have a good afternoon, and we'll be in touch. Take care. Bye-bye.
Bye.